Hello everyone, this is Dhanush Varma. I'm going to present my final project of recurrent neural networks for sequence data. So coming to the introduction, recurrent neural networks are a type of artificial neural networks designed for sequential or time series data, commonly integrated into applications like Siri, voice search, and Google Translate. Unlike traditional neural networks, recurrent neural networks leverage information from past events to influence current outcomes, making them well suited for tasks such as translation, natural language processing, speech recognition, and captioning. However, they face challenges like difficulty considering future events in predictions and sharing the same weight parameters across all network layers. LSTM, which is also called as long short-term memory, a special RNN architecture, addresses these issues by introducing a memory cell that can store information over long sequence. LSTMs utilize input, output, and forget gates to control data flow, allowing them to maintain stability, control state propagation, and remember long-term dependencies efficiently. This makes LSTMs particularly effective for learning complex time-based models, making them ideal for tasks like processing weather and climate data, where past weather patterns influence future forecasts. This final project report includes information about the time series data, which we use Delhi weather forecasting as a data set, and will generate a sine wave using a simple RNN, and also discuss about the vanishing and exploiting gradient problems uh, and limitations of simple RNN as well by building and also we build an LSTM model using time series data, and we redesign it and then compare the performances of the models. And yes, this is the introduction about the whole project basically. So in the next part, which is table of contents, it is divided into 6 parts, where in each part we talk about each topic. In the first one we talk about the data set, in the second one we talk about RNN with sine wave data, in the third one we talk about LSTM neural network, and in the fourth one we talk about LSTM with time series data. In the fifth one we talk about redesigning of the neural network, which we perform the same process in the previous LSTM with time series data, but we make a few changes and redesign it. And then in the sixth part, we just compare the fourth and fifth part and give an analysis of the performance. Yes. So let's talk about the first part, which is about the dataset. So the Delhi weather forecasting is the name for the dataset, which is spanning from January 1st, 2013 to April 24, 2017, which offers a rich time series of meteorological observations in Delhi, which is located in India. It has four major key variables, which is date, which represents the recorded day of weather data, and mean temperature, which indicates a typical daily temperature in Delhi, and humidity, reflecting the ratio of actual water vapor content to its maximum capacity at a given temperature, and wind speed, denoting the measured wind speed in Delhi, and mean pressure, which represents the average air pressure on a specific day. This dataset provides a comprehensive insight into Delhi's atmospheric conditions, serving as a valuable resource for developers training machine learning models tailored to India's climate. Utilizing this dataset enables the construction and refinement of models for more accurate weather forecasts in region. And coming to the data structure, so this data this data structure of uh, this data set is defined in a table style and also called as a data frame, where each row represents a specific data, which each column represents a different weather parameter. The column represents like average temperature, humidity, wind speed, and average pressure, which are the variables of the main parameters, and which is collected with numerical values for each day. And I have split the dataset into two, where I have used I have split the one dataset with the time series of 2013 to 2015, and the other dataset is with 2016, only 2016, where I've split the data and used the data 90% of the data for the training part, and the 10% one is for the testing part. So yeah, let's talk about the next part, which is RNN with sine wave data. So here, this process is like a guide for making a computer learn and predict future values based on a special type of data that goes up and down like a wave. First, we create and show this wave using a tool called NumPy. We organize this wave data in a near table and split it into two parts. One to teach the computer, which is also called as training, and the other to test how well it learned. So we then make sure the data is in a format that the computer can understand by using the tool called min-max scaler and another tool called time series generator, which helps in training the computer effectively. And next, we create the brain of a computer, which is called the model, where we use a tool called Keras. We tell it to use a special layer called simple RNN, which is good for learning patterns in this type of data. We also add another layer for predicting the next point in the wave. The computer is trained using a method called fit generator, going through the data 5 times, which is epochs, and learning from it. During this learning process, we check how well it's doing by looking at a graph that shows if it's getting better at predicting. Once it finishes learning, we test it on the other part of the data to see if it can predict new points in the wave. We then compare its predictions with the real points and make sure everything is in the right scale for easy understanding. Finally, we put the predicted points back into our data table and make the graph to see how well the computer did it in predicting the wave. This whole process is uh, done by using the tools like Keras and TensorFlow, which shows a practical way of making computers predict future values based on pattern they learn from special kinds of data. And coming to the and this is the output of the sine wave, which we can see on the slide in the right side. Yes. Coming to the next part, which is LSTM neural networks, where we're going to talk about the vanishing gradient problem right now. And the vanishing gradient problem is a big challenge in deep learning especially when training neural networks. To understand it, think of training as a process where a model adjusts its parameters based on calculating gradients. In deep networks with many layers, these gradients can become very small and they move backward through the layers during training. This is more prominent when actively functions squash their inputs, causing gradients and to approach zero. In simpler terms, when a neural network has many layers, the information about how to adjust its parameters can get lost, making it harder to train effectively. This is especially noticeable in recurrent neural networks, uh, which are designed for sequential data but struggle to remember information over long sequence. People have come up with ways to deal with the vanishing gradient problem. Uh, Specialized architectures like long short-term memory, which is LSTM networks, which uses memory cells and gates to help network remember or discard information, effectively solving the vanishing gradient problem. And coming to the next question, we are going to talk about explosive gradient problem. So the explosive gradient problem is an opposite challenge where the gradients become too large during training, causing numerical instability and disrupting the learning process. This happens when gradients grow uncontrollably as they move through the layers during backpropagation. To fix this issue, people use techniques like gradient clipping, where overly large gradients are scaled down to prevent them from causing problems. Additionally, careful weight initialization and batch normalization help maintain stability during training. In simple terms, the explosive gradient problem is when things get too big during training, and techniques like gradient clipping and careful weight initializations are used to prevent that. Here, next we are going to talk about limitations of simple recurrent neural networks. So, the simple recurrent neural networks, which are fundamental in handling sequence of data which have limitations. One one significant drawback here is they struggle to capture and remember information over long sequences, mainly due to vanishing gradient problem. They use the same weights for all time steps, making it challenging to capture long-term patterns in data. Their sequential processing nature makes them less computational efficient compared to other types of networks, especially when deadline in large datasets. Simple RNNs also face challenges with the sequence of varying lengths and can suffer from explosive gradient problem. Because of these limitations, more advanced architectures like LSTMs have been developed to address these issues and handle complex relationships with data. And coming to the LSTM networks, the next part, neural networks of LSTM, which is we have already talked about LSTM in the introduction. So LSTMs have a more complex architecture, including memory cells, gates that can help them overcome the vanishing gradient problem. They can efficiently handle tasks that require understanding context over extended periods, making them a crucial technology in the evolving field of deep learning. In simple terms, LSTMs are like upgraded version of simple RNNs, designed to remember information better and handle more complex tasks. And coming to the next part, we are going to talk about LSTM with the time series data. So here we are trying to build and train a time series forecasting model using a specific type of neural network which is called long short-term memory. Here I'm going to explain step-wise here. So for the first part, we're going to do the data preparation, where the code starts by loading the climate data set, which is already mentioned in the start, the Delhi's weather from the years 2013 to 2015. It's actually 2016, but I've split the data, one with 2013 to 15 and the other one is 2016. So here it explores this data set, checks the sizes and data types and more and some summary statistics. The next part we train and test split. So here the data set is divided into training set and as a testing set. So the testing set compresses to 20% to the total data used for validating the model's performances. In the next part, the data pre-processing, the selected attributes from the dataset is visualized as a time series plot to understand its patterns. The normalization is performed on the training and testing data using min-max scalar. This step ensures that the data falling within a similar scale, aiding the neural network in learning patterns effectively. And in the model building, the LSTM model architecture is establishing using TensorFlow Keras sequential API. So three LSTM layers are stacked sequentially, each followed by a dropout layer. So the dropout layer is a regularization technique used to prevent overfitting. The model is compiled with the Adam optimizer and a mean squared error, which is a loss function. So, and then the model is trained using a fit generator method with 10 epochs. Each epoch represents one complete pass through of the entire dataset. So, in the next part, the code visualizes the model's training performances by plotting the loss history over the training epochs. And then the trained model is used to predict values on the test set, and these predictions are transformed back to their original scale for comparison. And the visualization predictions where the original data training data and the model's predictions on the test set are plotted together for a visual comparison. Here in the forecasting, the model is further trained and the entire data set and then used to forecast for the next 366 days. The forecasted values are plotted alongside with the original data for an understanding of the model's predictive capabilities. So here the additional climate data for 2016 is loaded and then visualized. The forecasted values are combined with this data for a comprehensive view of predicted climate conditions. And in the conclusion, this code represents the complete workflow for developing an LSTM based time series forecasting model encompassing data processing, model creation, training prediction, and visualization of forecasted results. And coming to the next part, which is redesigning the neural networks. So here in the redesigning of the neural networks, we pretty much do the training and testing process as same, but we make few changes here where I would like to mention the previous data with the percentage of the data here for the first one is 0.2 and the layers of the LSTM is 3. The number of neurons in each LSTM layer is 50, and the length of the time series input sequence is 60. Batch size for training is 32, and number of epochs here is 10. But in the next one, here we can see the changes where the number of neurons is 120, whereas it was 50 in the previous one. And also, if we see here, the batch size and the length of the time series input sequence is same, but the number of epochs here has been changed to 15 from 10. So coming to the explanation here, the training cycle is used for 15 cycles, where the epochs is 15, as previous one is 10. And early stopping is used to monitor training progress and avoid overtuning. And yeah, it should be noted that 10% of the data is reversed for testing and 90% is used for training. The min-max scaling is used to normalize the data and ensure a uniform range of each function. The long short-term neural networks, which is suitable sequence-based prediction tasks, is then trained using a time series generator. Here, the time series generator is then used to make predictions about the test set, and the results are transformed back to the original scale. The model is retrained for forecasting the entire dataset, and the time series forecasting occurs over the next 366 days. As I've already mentioned, the process of the training and testing the dataset is same, and the model is also, the final output model is also almost same, but we can see few changes in the output, where I'll be showing you the previous output of the, where we can see the forecast line has a curve, and now in the second neural network, the model is having a forecast line of a straight line. So the curve which we have seen has disappeared and become the straight line, as we have made few changes after redesigning. And in the next part, let's compare the network performances. We can see few differences here in the values after comparing both the networks with a change of values. In the first network layer, it has one 0.2 drip layer. To avoid overfitting, deletion is an adjustment technique that randomly resets some inputs units during training. And in the first layer, in the first network, we have used 50 neurons form one LSTM layer in this structure. Recurrent neural networks of the long-term, short-term memory type are designed to capture long-term dependencies of sequence. The 50 neuron represent the number of processing units or memory cells in the LSTM layer. In the second network, the continuity layer, which has only one, where the discontinuity layer has the percentage of 0.3 to prevent the overfitting, and this drops layer like the first one and adds randomness during training. And coming to the dense layer in the second network, it is not explicitly stated but assumed to be comparable to original network in terms of regression. Here 120 neurons form on one LSTM layer in this structure. The second network has a more complex LSTM layer due to the increase in the number of neurons, which is from 50 to 120, which can enable the uh, detection of more complex patterns in time series data. The actual comparison where we can see is the first network has a quit rate of 0.2, while the second network has a quit rate of 0.3, which is more aggressive. Regularity is usually associated with higher dropout rate, which can prevent overfitting but can also slow down the training. And coming to the complexity of the networks, in general, the second network is more complex due to its higher dropout rate and larger number of LSTM neurons. The complex data patterns can be more difficult to capture, but may require but so uh, let's talk about loss function, where the loss function is mean squared error is often used when performing regression tasks such as predicting numerical values from time series data. Here, coming to the training period, it has 10 time periods are used to train the network. This shows that during the training, the network goes through the entire training dataset 10 times. In the second network, it 15 epochs, where that uh, it uh, where assuming that the periods during the training, the network gone through the entire the training data set like 15 times. And these are the differences which I have seen and I have observed while comparison the performances. And let's talk about, yeah, as I've mentioned, the curve here forecasts. The line forecast is the previous one, and in the second one the forecasting line is a straight line after redesigning the data network. And coming to the summary, here, the presentation begins by introducing a Kaggle dataset with which is Delhi weather forecasting, which covers meteorological observations in Delhi from 2013 to 2017, which provides valuable data from machine learning models tailored to India's climate. The subsequent sections delve into an applications of neural recurrent neural networks in weather forecasting. The first demonstrates a simple RNN using TensorFlow and Keras with a sine wave dataset, highlighting the model's architecture and visualization for predictions. The following section explores the vanishing and explosive gradient problems in RNNs, emphasizing the limitations of simple RNNs and introducing the long short-term memory networks as a solution. In the fourth part, applies LSTM to Delhi's meteorological data, detailing data processing, network architecture, and forecasting. The fifth section redesigns the neural network, adjusting hyperparameters for comparison. And the final part summarizes and compares two networks, emphasizing dropout rates and LSTM neuron count variations. This comprehensive exploration provides insights into weather forecasting using deep learning and addresses challenges in capturing temporal dependencies. And this is the summary. Thank you. This is the whole presentation is ended.